Why should we learn this concept? So where do you think that these stack operations, flag register instructions are held? These are tremendously used in advanced 8086 programming. We being a Java programmer or a programmer of Python, we many times we keep on using stacks without our knowledge. Stack operations are widely used and we won't be knowing. Whenever we make a function call and whenever there is a recursion, definitely the stack comes into the picture in the background. We won't be knowing about it. Being a programmer at an interface, we have an interface of Java programming and we don't know how the Java is dealing with the stacks. But in the background, every high-level programming language like Java or Python deals with the stack operations. Of course, also deals with flag register. But in 8086, we have an advantage of playing with stack memory and flag register. There are tremendous advantages. So, all the advantages, whatever we had with stack and flag registers will directly come into the picture. You can control the entire process if you hold the stack memory. And at the same time, we can also control the process. Process control, we can do it using flag registers. The principle is very simple, first in, first out, and we have two famous operations in stack. One is push and other is pop. Okay, we have tremendous applications on stack. One simple application is undo operation. For an example, in the word, if you type something, you know that controls, that means undoing thing. Undoing thing means if you don't want the current thing that is done by you, and if you want to go to the previous state, you simply press Control Z. How do you think that the previous state of your Microsoft Word is stored somewhere else? That somewhere else is none other than stack. Every status, the program status, is stored in stack. It means that if you want to get back to that particular state, you can do it at any point of time. That is the advantage. That's a simple example. So this is possible just by using stack. Not only this application, WhatsApp inbox is also a stack. Most recently messages you can see in the top. Tremendous applications in the field of computer science. To start up the mobile or to start the computer, we use stack. We use an operating system level bootstrap program. And also in data structures, we have learned expression evaluation. All these are applications. Depth first search can be implemented using stacks only. Knowing all the advantages in 8086, during your program, if you want to save the current state somewhere else, that somewhere else is none other than stack, you can save it. That is the advantage that we have in 8086. Now we'll see how this push and pop operation can be used directly inside 8086 program. So I'm highlighting the point here. Look at here. Push BX. So I have taken BX as an example. It could be any register, but the rule compulsory 16-bit register only. We have 4 register A, B, C, D. AX, BX, CX, DX are 16-bit registers. AL, AH, and so on are 8-bit registers. Here, compulsory it is BX. If not BX, it should be CX, AX, DX, anything else. But it should be 16-bit only. So what do you mean by that push BX? What do you mean by what exactly you are trying to do? Whenever you write this instruction inside the programming, inside your 8086 program, what it does? Very simple. BX is 16-bit data. It holds 16-bit data. That 16-bit data, it is stored in top of the stack. At any point of time, if you want that particular data, you can retrieve it by performing a pop operation. That is the advantage. Syntax is very, very important. Look at here, the second instruction, push 4597. 4597 is a value here. It's a value. 4597 is coded in hexadecimal. So it is a 16-bit data. 16-bit data you cannot directly push into the stack. This is invalid because look at this keyword. Immediate addressing mode is not possible in stack operation. Very, very important. Okay, at any point of time during your Viva, somebody may ask you, can I do it? Push 1, 2, 3, 4 hexadecimal value. No, your answer should be no. Because push followed by register name only as per the syntax of push operation. You cannot give a value directly because immediate addressing mode is not possible in stack operation. What is pop operation? Very simple. Whenever you want something inside your program, then you perform pop operation. What it does? Pop operation gets the topmost 16-bit or 2 bytes of data from stack and gets inside your program. You do whatever you want with that particular data. Getting data from stack is pop. Storing some data into the stack is push. I have written here the same rules. Whatever the rules that we have seen here, these two rules, the same two rules are applicable for pop operation as well. This is a stack segment, because as I'm going to talk about stack operation, it means that you should have the complete knowledge of stack segment. We are going to play with this particular memory. Where do you think your stack data is stored? In stack segment. There are 4 segments. In our last class also we have discussed one of the segments, one of the 4 segments is stack segment. If you want to store something into the stack, or if you want to get something from the stack, you need to know something about stack segment. In stack segment, there are 3 pointers that are used, or 3 registers, 16-bit registers. Stack segment SS, the very first one, is a segment register. BP, SP. BP, base pointer. SP, stack pointer. These two are used inside. These are offset registers. These two are offset registers to travel from this direction to this direction, or from bottom to up within this particular segment. BP or SP are used. This is segment inside your complete main memory. Where exactly the stack segment started will tell you this base pointer, and stack pointer is used to access your stack data, right? So because this picture is very, very important, you have to understand this stack segment. Otherwise, understanding stack operations is highly impossible. Look at here. This is your stack segment. Okay. So I've taken some addresses for our convenience. I've taken some addresses. The starting address of the stack segment is 2000. The next address 2001, 2002, and it goes on. Okay. 2018, 19, 2020. Let us imagine it's a very small stack segment which has only 20 addresses. That means at each address, you can store 1 byte. This point is clearly demonstrated inside the classroom, many times inside the lab. I already told you, at each address location, we can store only 1 byte of data, not more than that. This is true in any case. That means it is true in 64-bit machines, 32-bit machines. At every address location, you can store only 1 byte of data, not more than that. Right, good. This is the base pointer. Base pointer inside the stack segment always points to the starting address. This is this stack pointer. Stack pointer always points to the last address. The last address of the stack segment is 2020. Stack pointer points to the 2020. The last address cannot be used. Actually, this particular address location cannot be used. Imagine your stack program. Imagine the topmost variable, top variable. What is the initial value that you give for top variable? In most of the cases, you try to give -1, top equals to -1. And the moment you want to insert any value, you will say that if it is an array A of plus top, that means pre-incremented value of top, that -1 becomes 0, and you keep on inserting the values. Okay, the same case here, also the same case. Here we have a stack pointer pointing to this particular location. You cannot insert value here. You will start inserting values or pushing values from here. Okay, your stack pointer goes upwards. I repeat, your stack pointer goes upwards. Anyhow, that we will see in the next upcoming slide. The stack pointer points to the last addressing location. Base pointer points to the first addressing location. Then the moment you are talking, the moment you came to know that these 2 pointers are used, why 2 pointers? Why not it is simply 1 offset pointer? Why 2 pointers are used here? This is the first doubt that you should get. Look at here, when you keep on inserting some values, your stack pointer will be somewhere else like this. Okay, imagine that you have inserted some values up to here, and your stack pointer is at this particular location now. And it's very important for any programmer while doing the program to know whether the stack is empty or not. How do we know that stack is empty or not? It is nothing but the difference between the address locations of SP and BP, these two. If you find out the difference between BP and SP, obviously you will be knowing the amount of stack segment that is left over for you, because one of the biggest problem of stack is that stack overflow. At any point of time, okay, at any point of time, when you keep on inserting the values, you will come to 2000. After 2000, there is no stack segment. There is no stack segment. There you will get an exception called as stack overflow. So that's why at each time in the application, we need to check whether the enough amount of stack extent is available or not. How do we know the amount of stack memory that is available? SP minus BP. SP minus BP will tell you how much stack memory is left over. In the upcoming slide, we will perform push operation and pop operation on this particular segment, and we will see how the instruction can be used. It's very simple to understand. So before that, you look at here, BP is at starting point and SP is at the ending point. This is the two important points that I wanted to convey from this slide. I hope you understand, and we'll go to the next slide. Before that, look at here. While performing push operation, SP value increments. Why while performing push operation, sorry, the SP value has to be decrement. While performing pop operation, the SP value has to be increment. That anyhow, that I'll please ignore these two statements. I'll tell you these two statements with an example. Look at here now. So in this slide, we are going to perform a push operation. To perform push operation, I have written two simple instructions, 8086 instruction. Move BX1234, it's an hexadecimal value, 16-bit hexadecimal value. BX is a 16-bit register. Why I have used 16-bit register for push operation? That is the rule. Stacks can only obey 16-bit data at a time. It cannot accept 8-bit data or 1-byte data in case of 8086. Okay, that is the rule. That's why I have used BX. Okay, right, very good. Now, this is our BX register, 16-bit register, BH as well as BL. Okay, we have two, 8-bit, 8-bit. 8 plus 8 is 16-bit register. And 1, 2, 3, 4 is stored in BX register. You know very well, many times I told you, 1, 2, 3, 4, the lower byte. Okay, lower byte stores in the lower level register, that is BL. The higher byte, that means 1, 2, stores in BH. BH, BL. Lower byte, higher byte. So 1, 2, 3, 4 is available in register BX now. And then I wanted to push this value 1, 2, 3, 4 into the stack for some reason. For some reason in my program, I wanted to store this BX value inside the stack. For that reason, I have written push BX. If you are a normal programmer, you can learn this concept push BX and you can leave this concept right here. But if you wanted to know, if you wanted to become a very good programmer of 8086, now onwards, whatever I am going to teach, that will help you. Look at here now. So when you write this push BX, what is happening inside? What is happening inside, that you need to understand. Look at here. This is your stack segment that we have seen in our previous slide. Okay, starting address is 2000, 2001, and it goes on up to 2020. Your stack pointer initially pointing to the address 2020. I already told you that this address location cannot be used for push operation, and these remaining addresses can be used. Okay, right now I have performed push BX. That means 1, 2, 3, 4 has to be stored in stack. Okay, like this. The same rule, this is your BX register, 1, 2, 3, 4. This is higher byte, this is lower byte. How do you think this 16-bit data is stored here? I already told you that storing is done from bottom to up in this direction, bottom to up. So 1, 2, 3, 4, 1, 2, 3, 4. The higher byte stores in higher address. That means in 2019, the higher byte is stored. The 34, this is lower byte of the 16-bit value. The lower byte stores in the lower address, 2018. 2018 is lower address when compared to 2019. That's why 12 is stored here and 34 is stored here. Our 16-bit data is stored in two different locations, I mean two immediate locations, 2018 as well as 2019. Since you have stored something into the stack now, for every push operation, your stack pointer has to be moved upward because it has to point. Now your stack pointer is pointing to 2018. This is the topmost element. Of course, whenever the stack wants to access, it not only access 34 but also access 12. These two locations, that means SP as well as SP minus 1, these two locations will be accessed to get back the value 1, 2, 3, 4. Now we'll see the internal operations that happen during this stack push operation. What is happening here? I've written these three operations are happening inside in the background. While writing the program, we don't write these operations. This is just for our understanding. This is our BX register. Who is getting what? BH means 12 value is stored where SP minus 1. What is SP? Initially SP is 2020. SP minus 1 is 2019. Okay, in 2019 of stack segment, what are you storing? The value 12. Very good. This is done now. Now in the same way, BL. Who is getting this BL value? SP minus 2. What is the current value of SP? 2020. Minus 2 is 2018. Okay, so here is the place where you are storing the value 34. Right, good. So after performing this push operation, what is the last task that has to be done? You need to update your SP, because since you have performed push operation, you have to increment SP value. How many times? 2 times. You have to decrement the SP value. You have to decrement the SP value because the push operation is happening towards bottom to up. You are going this way. So 2020 has to be decremented. How many number of times? 2 times, because you have stored 2 values here. I mean, the 16-bit value is divided into 2 values, 12 as well as 34. That's why you need to decrement the S. What I wanted to convey very one simple point here. The SP value decrements for every push operation. I repeat, the SP value decrements by 2 for every push operation. This is the point that I wanted to convey with an example. I hope you understand the point. Okay, if you just learn push BX with syntax, that won't help you. If you know how this entire storing process happens inside the computer, then you can start playing with stack operation. Believe me, you'll become a very nice programmer in case if you know these 3 internal operations, whatever that is going to take place inside the stack. Okay, these 3 operations are very, very important. Okay, I hope you got the point. Now we'll see how pop operation happens. Okay, once if you understand how push happens, it's damn easy to understand how pop operation takes place. Okay, this is your stack segment. Stack segment starting at just 2000, 2001 and goes on up to 2016, 17, 18, 19, 20. Initially, your stack pointer is pointing to this location 52. That means 2016. Just imagine that you have already some existing data in the stack. 42, 36, 76, 52. Okay, 52 is the most recently entered data. That's why SP is pointing initially to this particular location. Right, very good. Now, I wanted to pop some data from stack to register BX. BX is a 16-bit register. It means that you are going to pop 16-bit data. 16-bit data means not only 52, but also 76. This 76, 52, these 2 values will be popped and will be stored in BX. How? Very simple. Higher byte in higher address. What are the values there? You please store in the higher byte. Lower address, what are the values there? You store in the lower address. BX is a combination of 2 registers, BH as well as BL, lower byte, higher byte. Since you are performing pop BX, it means that from the stack you wanted to pop 16-bit data and store in BX. You are telling the computer to store 16-bit of information of stack, topmost 16-bit data to BX register. So your computer is doing that. How? 76 is stored in BL. 52 is stored in BL because 52 is the lower address and the higher address is 2017. 76 is stored in BH this way. 76 is here, 52 is here. So the exact value that I wanted to pop is 7652. The value that I wanted to pop is 7652, right? So what are the 3 internal operations that takes place during pop operation? Very simple. Who is getting what? BL is getting the value. From where? From the value SP, from the location SP. From the location SP, BL is getting the value. So BL 52, this is the location. This is the instruction. When executed, this value comes and stores in BL. Okay, right. So who is getting what in the next operation? BH gets the value 76. From where? SP minus 1 location, 2017, the value 76 travels this way and stores in BH. Okay, so SP plus 1, that means 2017, this value is stored in BH. This is the instruction. And what is the updation that you need to do at the end? Since you have performed a pop operation, these two are not available, no more available in the stack because you performed a pop operation and you came to this location and stored that particular thing in SP plus 2. I mean, you have to update this SP to SP plus 2. Now your SP after pop operation, SP points to 2018. So this is what the push and pop operation, and understanding these 3 things are very, very important. And what is the conclusion point here is that SP increments for every pop operation. The stack pointer increments for every pop operation. Currently you are here. After performing pop operation, you came to here. It means that increment has taken place. Of course, incrementation +2 because every time 16-bit data has to be popped. That's why it is +2. This is the program to perform push and pop operation. I've taken a very simple example. Whatever I have explained so far is coded. Okay, right. So this is the code segment. Inside the code segment, I have taken these 3 instructions are very important. Remaining rest of the instructions you already know. You already done this rest of the instructions during your lab time. So I wanted to concentrate on these 3 instructions here. I have highlighted here. Move bx, comma 1, 2, 3, 4. 16-bit data I am storing in bx, and that 16-bit data I am storing in stack. Whatever the topmost 16-bit data that is available on stack, I'm popping into register CX. Okay, so initially CX and BX are 0 at this particular point of time. During the startup, CX is 0, BX is 0. Now, when executed this one, BX becomes 1, 2, 3, 4. CX is still 0. Push BX. Stack will get the value of 1, 2, 3, 4. And BX is still 1, 2, 3, 4. And stack will copy these values 1, 2, 3, 4 in it. So when I execute pop CX, before pop CX, CX was 0. After pop, 1, 2, 3, 4 has to be stored to CX, where your program is getting from that 1, 2, 3, 4, not from BX, but from stack. From stack, 1, 2, 3, 4 is copied to register CX. And now let me execute this program, emulate it. Right, we'll see line by line execution. Before I perform the execution, I'm just telling you that I'm going to use 2 registers, BX and CX, BX as well as CX. Don't mind, CX value is initialized to 5. CX is a count register. It takes some value always. So don't mind. Just imagine this value as 0. You don't ignore the existing value of CX. Okay, just imagine it as 0. Not a problem. BX is 0, CX is 0. We'll start line by line execution. The moment I execute this one, 1, 2, 3, 4, single step. So now BX has got the value 1, 2, 3, 4, 1, 2, 3, 4. BX got 1, 2, 3, 4. And now I wanted to execute push BX. Before that, I'm showing you the stack. This is the stack segment. 0710 is the stack segment address, and the offset 002A. Here, there is no value that is available at the top of the stack. Now let's push this BX into it. Okay, right, single step. Now again, let's see the stack. Because the BX has 1, 2, 3, 4, let's check 1, 2, 3, 4 has came into the stack segment or not. Let us see stack segment now. At the top of the stack, you can see that 1, 2, 3, 4 is available. Addresses, the even addresses, you can see FFFC, and then FFFD is not available, E is available, because at each location, 16-bit data is used. That's why you are seeing these address locations in an odd manner. A is there, B is missing, C is there, D is missing, E is available. Because at every address location, so 16-bit 1, 2, 3, 4 is splitted. 2 values is stored in E location and another 2 values are stored in D location. That need not to be represented here. That's why, as a simplicity, this even addressing is maintained inside this emulator. That's not a big deal. Anyhow, at the top of the stack, we have the value 1, 2, 3, 4. That's very important. Right now, I need to execute pop CX. Before pop CX, we have 0005. Of course, the 05 is the initialized value of counter. That's not a big deal. Now, after executing pop CX, okay, whatever the stack value 1, 2, 3, 4 is there, that has to be eliminated. That has to be eliminated from there and has to be copied to CX. Okay, let's execute it. Okay, now you see 1, 2, 3, 4 in CX. We got this value here. Okay, so that value was popped from the stack. The top of the stack 1, 2, 3, 4 is popped from the stack memory, and that pop, the value is stored in the CX register 1, 2, 3, 4. That's all. That's all what I wanted to discuss.